Imagine, for a moment, the possibility that our solar system is on the verge of encountering something profoundly unnatural. Currently, only a minuscule fraction of all potential interstellar objects that have ever passed through our vicinity have been detected, less than 1/1000th of 1%. The third such object, known as Atlas, is exhibiting behaviors that have left scientists utterly perplexed. In the span of the next 12 days, this awe-inspiring interstellar traveler, weighing in at 36 billion tons, is scheduled to make a close approach to our star, moving at a staggering 80 times the speed of a bullet. And it is precisely within this encounter that potential peril lurks. Atlas's trajectory is alarmingly aligned with the plane of our solar system, a phenomenon that stands in stark contrast to what one would expect from any random comet. This alignment prompts a deeply unsettling question. Is this an ordinary wanderer, or could it be a machine, designed with an intention to arrive at our star and halt within the confines of our solar system? While Earth's observational capabilities are hampered by the overpowering glare of the Sun itself, the only certainty we will have is what becomes apparent once Atlas has passed beyond the glare. The greatest danger lies in the unseen threats that may manifest at the most critical junctures. Atlas hurtles toward our star at an astonishing velocity, approximately 34 miles per second, following a route that seems to defy the very laws of probability. Its journey resembles that of a car entering seamlessly into the correct lane of a cosmic highway. Unlike the typical scenario where a random comet would approach with a steep, erratic angle, Atlas glides smoothly through the plane of our solar system, tilted by just 5 degrees from the ecliptic. This is the invisible disk along which our planets orbit, akin to a spinning coin suspended in midair. For an interstellar visitor, such a precisely aligned entry is an enormous statistical anomaly. Random arrivals should be scattered across the sky, with most missing the ecliptic by wide margins, much like balls thrown from every conceivable direction. The observed trajectory of this interstellar visitor presents a scenario so exceptionally rare it borders on the improbable. Its path appears to deliberately align with the established lanes traversed by our solar system's planets. It seems almost purposefully to have been mapped to blend seamlessly with the local orbital traffic, a phenomenon as astonishing as a driver navigating the complex rules of a foreign metropolis with flawless precision. According to detailed celestial mechanics models developed by planetary scientists, only infinitesimally small percentage of objects originating beyond our solar system should ever arrive upon such a path. The ecliptic, that grand celestial plane upon which the planets orbit, constitutes merely a thin slice of the vast celestial sphere surrounding us.
For an interstellar comet to approach within 5 degrees of this critical plane is astronomically akin to flinging a dart at a rapidly spinning globe and striking a precise city street. Technically conceivable, yet statistically bordering on the impossible. The previous 2 confirmed interstellar objects, designated Oumuamua and Borisov, arrived from considerably higher inclinations. Their trajectories slice through the solar system at markedly steep angles, much like aircraft flying perilously too high or too low relative to established airways. Atlas, in stark contrast, traces a distinct retrograde arc. It moves counter to the prevailing direction of planetary motion, yet maintains an astonishingly flat alignment precisely along the solar system's dusty disk, akin to swimming directly against a powerful current while remaining effortlessly close to the water's surface. This constitutes a near-perfect orbital maneuver, one defying conventional expectations. This remarkable alignment transcends mere astronomical curiosity. It fundamentally alters the possibilities during the object's closest approach to our central star, known as perihelion. An object arriving along the ecliptic meets the radiant heart of our solar system at a shallow angle. This specific geometry creates an extended window of opportunity for any proposed maneuver that leverages the star's immense gravitational pull. The effect is reminiscent of a skateboarder skillfully using a ramp to gain crucial extra speed and distance. If a spacecraft engineer, faced with the daunting challenge of propelling a vessel towards the outer solar system or beyond, sought to utilize the Oberth effect, a critical principle in astronautics that allows for amplifying the thrust efficiency of a rocket burn by executing it at the point of maximum velocity near a massive body like a star. This precise geometric configuration would be the optimal choice. Maximizing the proximity and duration of the close stellar encounter is paramount for harnessing this gravitational assist to its fullest potential, enabling missions that would otherwise be impossible with conventional propulsion alone. This alignment offers the ideal conditions for exploiting the Oberth effect's unique physics. The profound principle of orbital mechanics dictates that a spacecraft achieves significantly greater kinetic energy and trajectory alteration by firing its propulsion system while traveling at peak velocity within a deep gravitational well. This fundamental advantage, often termed the Oberth effect, explains why maximizing engine thrust during moments of greatest speed yields exponentially more change.
The trajectory of the recently discovered interstellar visitor, designated Atlas, appears meticulously aligned with this very maneuver. This precise configuration constitutes a striking anomaly, a major warning sign demanding scrutiny. Is this alignment truly a matter of pure cosmic coincidence? Or does it represent the most efficient trajectory conceivable for an object specifically engineered to decelerate? The statistical improbability alone, based solely on these calculated parameters, is sufficient to provoke significant skepticism and raise critical questions. Atlas was first detected on the first day of July in the year 2025 by specialized astronomical surveys utilizing advanced telescopes situated in the Chilean Andes. This detection confirmed Atlas as only the third verified interstellar object to have ever traversed our solar system. Its measured entry velocity, exceeding 124,000 miles per hour, unequivocally demonstrated that Atlas was not gravitationally bound to our Sun. This velocity profile confirmed its status as a genuine interstellar traveler, originating from beyond the confines of our local stellar neighborhood. Its closest approach to the Sun, known as perihelion, is scheduled for the 29th day of October in the year 2025. At this critical juncture, Atlas will pass at a distance of 1.36 astronomical units. This position places it remarkably close to the orbit of Mars, resembling the perilous act of navigating a narrow passage between two high-speed vehicles on a busy highway. Current orbital calculations based on established celestial mechanics indicate that Atlas will subsequently perform a gravitational slingshot maneuver around the Sun and then vanish forever into the interstellar void. However, persistent intrigue remains due to the object's unusual orbital characteristics. Its trajectory exhibits a remarkable alignment with the solar system's primary plane, the ecliptic, coupled with its distinctly hyperbolic velocity profile, a path signifying it came from outside the solar system and will depart permanently. This specific combination of orbital elements leaves an enduring enigma unresolved. Is this configuration the product of random cosmic chance, or does it constitute the unmistakable signature of deliberate intentionality? As the countdown progresses towards the pivotal moment of perihelion, the significance of the situation intensifies dramatically. If Atlas proves to be a natural phenomenon, it represents an exceptionally rare but fundamentally explainable astronomical occurrence. Yet, if its origins are artificial, the very geometry of its path suggests an extraordinary level of sophisticated planning and purposeful design that utterly transcends the realm of mere accident.
The defining moment of truth, the utilization of the Oberth effect at perihelion, will occur when Atlas is moving at a velocity approaching 42 meters per second. This speed surpasses 2 times the velocity achieved by the fastest man-made spacecraft ever launched from Earth, propelling Atlas through the void with the force and trajectory of a cosmic cannonball.
For a hypothetical spacecraft designated Atlas, contemplating the theoretical challenge of becoming permanently bound in orbit around our star, effectively transitioning from a high-speed escape trajectory, a hyperbolic path, to a stable, closed orbit, the Oberth effect provides a potential solution. The necessary maneuver involves applying a powerful retrograde thrust, an engine burn directed precisely against the direction of travel, timed to occur exactly at the point of closest approach to the Sun. The objective is to achieve sufficient deceleration at this critical juncture. By sacrificing velocity at the peak of its speed, the spacecraft could shed enough energy to fundamentally alter its entire trajectory, shifting from an open, escape path back towards the Sun into a closed, bound orbit. A maneuver conceptually similar to expertly braking a high-performance vehicle to skillfully maneuver it into a confined parking space. The efficiency gained at this peak velocity moment is the crucial factor making such a dramatic orbital capture feasible. Based on orbital mechanics, achieving a stable solar orbit at a distance of 1 3/10 astronomical units demands a significant reduction in velocity, specifically approximately 12 4/10 meters per second, precisely at the point of closest approach to the Sun. This requirement represents a formidable challenge. Even the most advanced chemical or nuclear propulsion systems conceivable would necessitate an amount of fuel approaching the very mass of the spacecraft itself. The situation resembles a car requiring an entire tank of gasoline weighing as much as the vehicle it propels. The Yarkovsky effect remains the sole method among existing technological capabilities that offers any realistic possibility for executing such a substantial orbital maneuver. While natural comets do experience minor trajectory alterations due to outgassing jets expelling vapor and dust, these forces are inherently weak, highly unpredictable, and rarely aligned with the precise vector needed for orbital insertion. Their influence typically results in velocity changes measured in mere meters per second, a difference comparable to the gentle push of a breeze rather than the devastating force of a hurricane capable of altering velocity by tens of meters per second. Conversely, a carefully orchestrated, precisely timed retrograde engine burn conducted at perihelion would produce an unmistakable signature within observational data. Astronomers monitoring the object's path following its passage behind the Sun would readily detect the resultant dramatic shift in its orbital trajectory. The definitive indicator would manifest as a sudden, step-like reduction in its exit velocity, continuing far beyond any adjustment explainable by natural outgassing phenomena, analogous to observing a car decelerate abruptly for no discernible reason.
This underscores the critical importance of the perihelion encounter window. Should a deceleration attempt be made during this phase, the Sun's immense gravitational field would act as a powerful amplifier, transforming a relatively modest applied force into a profound and permanent transformation of the object's orbit. The underlying principles governing this process are conceptually straightforward, yet the energy requirements involved are staggering. Ultimately, the focus shifts to vigilant observation, seeking any evidence that either natural processes or an unidentified agent possesses both the capability and the purposeful intent to exert such extraordinary influence.
The limitations imposed by proximity to the Sun affect space-based observatories just as severely as their terrestrial counterparts. The renowned Hubble Space Telescope and the advanced James Webb Space Telescope are all equipped with stringent programming that absolutely forbids their instruments from pointing within a 50 to 85-degree angular range of the Sun. This rigid constraint eliminates any possibility of obtaining observational data on Atlas during this critical period, even in the final moments before or after the event. Similarly, the Transiting Exoplanet Survey Satellite, known as TESS, despite its wide-field cameras capable of monitoring vast swaths of sky, remains constrained by the same solar elongation rules. Its observation protocols mandate closing its sensitive eyes to the Sun's brilliance whenever its position in the sky approaches too closely, much like instinctively shielding one's own eyes against intolerable brightness. This meticulously engineered avoidance mechanism feels, on a fundamental level, like a deliberate design. Atlas's orbital trajectory doesn't merely permit a dramatic change in course. It actively conceals such a maneuver from even our most advanced and vigilant instruments. The temporal alignment is flawlessly precise. If the singular objective were to execute a significant alteration in orbital path while remaining entirely undetected, the 22nd day of October to the 7th day of November in the year 2025 presents the exact optimal opportunity and location to achieve such an unseen transformation.
However, even from Mars, the object proved astonishingly dim, registering 50,000 times fainter than the satellite's typical targets. Preliminary images captured by the ExoMars Trace Gas Orbiter were subsequently analyzed by the European Space Agency team. Their assessment dismissed these initial findings as almost certainly instrumental noise or interference. The challenge of isolating such a faint signal against the background was likened to trying to photograph a single tiny candle flame burning brightly during a fierce blizzard. The faint object was hopelessly lost in the visual clutter. No confirmed detections were ever formally released by the scientific teams monitoring these missions. For now, the only definitive information available is the profound certainty of absence. The situation is comparable to attempting to watch a movie while the screen remains completely dark. This represents a multi-week interval during which any significant and dramatic change, whether arising from natural processes or unknown factors, could transpire entirely unobserved by our current network of space-based instruments. When the object reemerges near the dawn sky in November, astronomers will necessarily be searching for after-the-fact evidence. They will be piecing together fragmented clues, attempting to reconstruct the sequence of events that occurred during this period of scientific invisibility, a period dominated by the phantom mass mystery shrouding Atlas. Traditionally, brightness serves as a reliable indicator of mass for objects like comets. Photometric readings, calibrated against standard comet reflectivity measurements, had initially placed Atlas's estimated mass at approximately 36 billion tons. This figure would have made it one of the heaviest natural visitors to our inner solar system in recent memory. However, this fundamental assumption linking apparent brightness to physical mass is now critically undermined by the dramatic dimness observed during the crucial conjunction period. The situation is paradoxical, akin to discovering that a person who appears imposing and large in stature actually possesses no measurable mass at all.
Instead, the Mars Reconnaissance Orbiter, alongside the European Space Agency's Trace Gas Orbiter, reported no measurable perturbation whatsoever. The event felt akin to a colossal truck passing by on a highway, yet leaving not a single tremor detectable in the Earth's fabric. Comprehensive tracking records meticulously compiled by the Deep Space Network revealed absolutely nothing beyond the constant, low-level background noise, like straining to hear a faint whisper in an exceptionally quiet room and finding only silence. This absence of signal was not a matter of simple missed detections. The scientific instruments involved were operating at peak sensitivity. The lack of gravitational imprint stood in stark contrast to a previous event. In 2014, comet Siding Spring, which was significantly smaller and lighter than Atlas, executed a much closer flyby of Mars. Despite its smaller size, this comet demonstrably left a detectable fingerprint on the planet's trajectory. Therefore, the complete absence of any gravitational effect from Atlas, given its estimated mass being orders of magnitude greater, became profoundly perplexing. The discrepancy has not escaped the notice of the scientific community. Specialized astronautics teams have undertaken rigorous double checks of the orbital solutions, meticulously searching for any unexplained drift in Mars's motion or subtle anomalies in spacecraft signal timing that might betray the presence of Atlas's mass. The investigation has yielded a consistent and surprising answer. There is simply no gravitational tag, no residuals, no evidence whatsoever of a massive solid core exerting its influence. The situation is as inexplicable as encountering a balloon that appears heavy and substantial, yet, upon inspection, is filled only with air. This profound mystery has prompted several hypotheses among researchers. One suggestion posits that the mass of Atlas itself may have been significantly overestimated. Could the asteroid's observed brightness, the key factor used to estimate its size and thus its mass, be artificially inflated? Perhaps an envelope of fine dust surrounding the core, or an unusually reflective surface properties, akin to a person wearing clothes that make them appear larger than their true form, is deceiving the measurements? This possibility offers a potential, though still speculative, explanation for the enigmatic lack of gravitational signature. Some scholars propose that the comet might possess a hollow or highly porous composition, akin to a cosmic shell as opposed to a solid, dense body, comparing it to a ping-pong ball rather than a bowling ball. Analyzing periodic variations in its luminosity indicates that this celestial object rotates at a velocity exceeding what would be expected for a solid body of similar dimensions, much like a top spinning too rapidly for its material to be made from iron.
Thus far, the empirical data contradicts simple explanations. We are confronted with a luminous entity spinning swiftly with negligible gravitational force, leading researchers to entertain the hypothesis of a hollow shell, either a natural occurrence or a product of an unknown process. Spectroscopists monitoring Atlas in mid-September observed a coma stretching 111,000 miles, a gaseous and dusty envelope that eclipses the size of the nucleus itself, resembling a cloud the dimensions of a small country. Among the chemical constituents measured, hydrogen cyanide emerged as the predominant molecule, with a release rate of 4.5 times 10 to the power of 25 molecules per second, an astonishing quantity equivalent to approximately 4.4 tons of hydrogen cyanide vented into the void of space each second. This constant outflow of toxic gas, while notable for its magnitude among known comets, is not unprecedented. It's akin to encountering an exceptionally tall individual, remarkable yet feasible within the spectrum of known phenomena. The substantial size of the coma, coupled with the consistent hydrogen cyanide emission, hints at active outgassing triggered by the influence of sunlight on ancient ice deposits. As Atlas ventures closer to the heart of our solar system, jets of vapor and dust are projected outward, shaped by the influence of radiation pressure and the solar wind, culminating in an asymmetric halo that signifies both motion and volatility. Nevertheless,
The chemical composition of Atlas transcends mere scientific curiosity. It provides invaluable insights into the processes shaping its behavior and evolution. The essential composition of Atlas before its closest approach to the Sun establishes the fundamental benchmark against which its nature can be objectively evaluated. This pre-perihelion spectroscopic data, revealing specific concentrations of hydrogen cyanide, water vapor, and carbon monoxide, functions as a unique chemical fingerprint. It represents the crucial baseline measurement, our definitive before picture. This particular triplet of molecular signatures, hydrogen cyanide, water, and carbon monoxide, aligns perfectly with the established expectation for a natural comet, a volatile, porous, and icy snowball traversing the solar system. Obtaining this data is paramount because it provides an indispensable control variable. If Atlas is indeed a conventional comet, its fundamental composition should remain remarkably consistent after its close solar encounter, experiencing primarily surface-level alteration akin to being gently warmed. The presence of these specific molecules, particularly hydrogen cyanide, alongside traces of water and carbon monoxide, firmly places Atlas within the well-documented territory of solar system comets. Spectral signatures observed match those cataloged in previous interstellar visitors, lending further support.
However, the relative proportions and intensities of these spectral features hint at a potentially unique formation history, much like a familiar recipe prepared with slightly modified ingredients. At present, Atlas's observed behavior strongly supports a natural origin. It demonstrates characteristics consistent with a volatile, rich, porous body undergoing mass loss as solar heat causes its ices to sublimate, analogous to ice melting under intense warmth. This meticulously measured baseline, captured before the critical solar encounter of perihelion, will serve as the definitive reference point. Any significant alterations to its chemistry or fragmentation patterns observed afterward will be judged against this detailed spectroscopic record. Deviations from this established September recorded profile will stand out starkly, akin to false notes disrupting a perfectly composed symphony. The hypothesis proposing Atlas possesses a hollow internal structure racing toward our star presents a significantly more complex physical scenario. This isn't merely a theoretical puzzle. It constitutes a scenario with concrete, testable consequences. It effectively describes an experiment that can be proven or disproven through observation. Contemplate the implications of a structure designed not for endurance, but for transformation, potentially unfolding or collapsing in specific ways under solar influence. When a comet reaches its perihelion, the point of closest approach to the Sun, the intense solar radiation and powerful gravitational forces present the most severe stress of its entire journey. Under such extreme conditions, a comet's fragile nucleus might simply succumb to the strain and disintegrate spontaneously. This natural fragmentation would likely scatter debris in unpredictable, chaotic directions, forming a cloud of material following paths governed solely by gravity and initial breakup forces. However, beyond this inherent vulnerability, scientists entertain a more intriguing prospect. They consider the possibility that an artificial structure, designed specifically for this purpose, could exploit the unique conditions of perihelion. Imagine an intentional deployment orchestrated with precision, unfolding like a flower, opening its petals at the exact, critical moment. For such a designed entity, perihelion offers a singular opportunity for action. Instead of a random, uncontrolled breakup, the structure's shell could be engineered to release smaller, independent units, probes or sensors, each assigned its own distinct trajectory.
Picture them dispersing like dandelion seeds carried on a breeze, yet each following a carefully calculated path. This scenario presents the ultimate test. Nature, operating without design, produces disorder. A naturally braking comet generates a cloud of debris whose movements, while chaotic, generally follow similar gravitational patterns. Intelligence, however, introduces order.
It establishes deliberate patterns. It creates specific vectors and velocities that defy the simple drift expected from natural processes. In this instance, the evidence for intelligent design would be tangible and undeniable. Post-perihelion, astronomers would search for discrete, non-random trails radiating from the original path. These would resemble carefully choreographed firework bursts, exploding in specific patterns. Some fragments would be observed accelerating or steering away from the star, not merely drifting passively under gravitational influence. Patterns within the debris field would emerge as unmistakable signatures. Straight lines of travel, sudden, sharp changes in velocity, or clusters of fragments moving in concert as if under precise control. Such deliberate arrangements would starkly contrast with the background of natural chaos. Dr. Galileo Loeb's project is meticulously preparing for this exact scenario. His research checklist is unequivocal. Every outbound fragment must be tracked meticulously. Each fragment's velocity must be measured with high precision. Finally, these measurements must be rigorously compared against established models of natural comet breakup, seeking the telltale signs of artificial orchestration. The cosmic stage was set for a pivotal observation. The proximity of celestial bodies offered a fleeting window of opportunity, but the outcome hinged entirely on the nature of the data captured. If the gathered information proved chaotic and devoid of discernible structure, the entire observational scenario would collapse into insignificance. However, should the skies reveal patterns and order amidst the darkness, the implications would resonate profoundly across the scientific community. This prospect felt akin to discovering intricate, purposeful footprints on a vast plain, instead of a random scattering of tracks left by countless passing creatures. The critical period following perihelion, the point in the orbit where a celestial body comes closest to the Sun, would determine which narrative the empirical evidence ultimately supported, particularly concerning the missing imagery from Mars. The effort focused on the lost images from Mars. The ExoMars Trace Gas Orbiter, specifically engineered to scan the Martian surface for atmospheric gases, was ingeniously repurposed during the Atlas comet's close approach to Mars in early October. Observing the distant comet from Mars's orbit was comparable to attempting to use the finest microscope to discern the distant stars scattered across the night sky. The instrument team redirected their high-resolution camera, meticulously trained on planetary details, towards the seemingly empty void of space beyond Mars. They captured a series of exposures, each meticulously timed for 5 seconds and pushed to the absolute technical boundaries of the instrument's capabilities.
The target comet presented an astonishing challenge. It was nearly 50,000 times fainter than any object the orbiter was originally designed to detect. This extreme faintness evoked the image of attempting to photograph a solitary candle burning miles away, its light almost lost against the vastness. The initial raw frames, upon return to Earth, offered little more than a sparse distribution of digital static or noise. In the vast majority of these images, the anticipated comet signal was entirely indistinguishable from the inherent background noise permeating the sensor data. It was like searching for a single specific needle within a massive, chaotic haystack composed entirely of pixels. The sophisticated processing pipelines, meticulously calibrated and optimized for extracting sharp and detailed signals from Martian terrain, struggled profoundly to isolate any reliable indication of the comet's presence.
It was a process comparable to attempting to sift fine sand using a coffee filter. The tools were simply not designed for the task. Analysts at the European Space Agency examined the preliminary processed images and concluded they were likely contaminated by noise. They were not sufficiently confident to assert even the possibility of a weak detection of the comet in these initial results. The challenge extended beyond the mere faintness of the target. Mars orbiters possess limited bandwidth for transmitting data back to Earth. These valuable communication windows are highly contested resources, competing fiercely with other critical planetary science priorities. Furthermore, the downlink process itself creates significant bottlenecks, meaning each batch of images must wait its turn. Before these precious data packets even reached the public archives, they passed through multiple layers of meticulous calibration, necessary data compression, and thorough scientific review. The journey of the information, from sensor to public record, resembled the passage of a handwritten letter through numerous intermediaries before finally reaching its intended recipient. The unprecedented proximity of this celestial body, Atlas, to our Sun, as observed from Earth, created an insurmountable obstacle for verification against ground-based data. By the time the processed information became publicly available, scheduled for the 11th month of the year, a substantial period had elapsed since the object reached its closest approach to the Sun. This critical gap presented a significant risk. Any abrupt alteration in Atlas's path or physical structure could have occurred unnoticed during this blackout window. The analogy is stark, like missing the most crucial scene of a film simply because one was momentarily absent from the viewing area.
For analysts scrutinizing the data, each ambiguous pixel held profound significance. It represented a poignant reminder that the pivotal moment of discovery might be concealed within the inherent noise of the observations. The vital clues, if they existed at all, could have arrived so belatedly that capturing them in real time was rendered impossible. The scientific implications of successfully capturing such a body were staggering. A natural object originating from interstellar space being gravitationally captured by our Sun would fundamentally rewrite the established principles of planetary science. This discovery would be akin to uncovering an entirely new law governing the physical universe. For researchers, it would signify the acquisition of the very first permanent sample of material from beyond our solar system. This unique object would become a subject of study for countless generations, effectively bringing a tangible piece of another world into our cosmic neighborhood. The potential even existed to launch a dedicated mission to investigate it directly. However, this profound scientific excitement was tempered by a deep and unsettling sense of apprehension. A persistent question lingered: what if Atlas was not merely an inert rock? For defense planners and intelligence agencies, the scenario transcended mere academic curiosity. Internal documents circulated within prominent organizations such as NASA and the United States Space Force during the period when surveillance was compromised outlined contingency models. These hypothetical scenarios considered the possibility that the object might have utilized its perihelion approach in a highly sophisticated manner, potentially employing an engineered burn to deliberately reduce its velocity. If such a scenario was suspected, established surveillance protocols were designed to escalate dramatically, mirroring the increased security measures implemented when a potential threat was identified. Despite these internal preparations, no official public guidance or formal threat assessments had been released by any agency addressing this specific situation.
However, amidst the pervasive speculation surrounding such extraordinary claims, empirical evidence remains the paramount arbiter. To critically assess these possibilities, observers require a rigorous and clearly defined checklist of observable phenomena. The initial step demands vigilant monitoring for a sudden, unambiguous change in the exit velocity of the object, coupled with a distinct and abrupt drop in astrometric residuals. Crucially, This change must be demonstrably unexplainable by the natural process of cometary outgassing, which can mimic similar effects. The subsequent phase involves scrutinizing the object's aftermath for the presence of organized debris fields, discrete trails, or individual fragments exhibiting acceleration patterns in non-random directional vectors. This stands in stark contrast to the chaotic, unpredictable dispersion characteristic of a natural structural breakup event. A vital verification step requires cross-referencing any findings with historical records of atmospheric anomalies, particularly reports categorized as Unidentified Anomalous Phenomena, UAP events. These records should be examined specifically for instances synchronized with the object's closest approach to the Sun, known as perihelion, effectively connecting previously unlinked data points in a complex cosmic puzzle. The critical data sets to be meticulously observed encompass a diverse array of publicly accessible sources: ground-based and space-based optical telescopes, radar installations, specialized polarization studies, and dedicated citizen science occultation campaigns conducted primarily in the Southern Hemisphere. Potential recovery images, precise trajectory solutions, and unprocessed sensor data gathered from archive channels associated with major space agencies and projects, including NASA, the International Space Agency, the ISA, the Chinese National Space Administration, the CNSA, and the Galileo Initiative, are slated for public release during November and December of the current year. The fundamental principle governing this investigation remains strict falsifiability. If the trajectory analysis reveals no discernible step change in the exit path, if observed fragments drift in random directions without coherent acceleration, and if no correlated atmospheric anomalies manifest, the prevailing explanation reverts to natural causes. The ultimate test is not merely what is theoretically possible, but specifically what the accumulated data conclusively confirms. This process mirrors the methodology of a skilled detective who relies solely on tangible evidence, not hypothetical theories, to reach a definitive conclusion. The Chronicle of Celestial Events confirms that on the 29th day of the 10th month in the year 2025, the enigmatic object designated Atlas will attain its closest approach to the Sun, known as perihelion.
This precise moment will see it positioned at a staggering distance of 36 astronomical units from our star. This astronomical occurrence is substantiated by meticulous examination of both Atlas survey records and trajectory data meticulously maintained by NASA. Furthermore, Atlas's trajectory exhibits a notably near ecliptic path, approaching only 5 degrees above or below the ecliptic plane, the fundamental plane of planetary motion. Orbital models developed by astronomers calculate that such a pronounced near-ecliptic approach for an interstellar visitor is a statistically rare event, akin to winning a cosmic lottery, despite the inherent improbability. Preliminary photometric triage estimates utilizing light reflection measurements suggest an immense mass for Atlas, potentially reaching 36 billion tons. However, this calculated mass presents a significant discrepancy when compared to observations from its close approach to Mars on the 3rd day of October. During this Mars flyby, no detectable gravitational perturbation was registered, a finding that contradicts the expected influence such a massive object should exert. This inconsistency is documented within the official records maintained by both the International Space Surveillance System, ISA, and NASA's navigation databases. Complicating the matter further, there exists a period of complete observational silence, known as superior conjunction, when the Sun directly blocks the line of sight to Atlas.
This critical window, during which vital data could have been gathered, coincided precisely with published telescope scheduling conflicts, effectively forcing astronomers to close their eyes at the moment of maximum importance. To date, no classified defense advisories or market alerts have been issued concerning the possibility of Atlas being captured by our solar system or possessing an artificial engineered origin. Its true nature remains an open question. Is it a vast, porous comet, or perhaps something entirely designed? Resolving this mystery will likely require careful analysis of post-perihelion debris patterns and any discernible velocity changes expected to manifest within datasets collected in the late November timeframe. This process is likened to waiting for the results of a crucial medical examination, where definitive answers arrive only after careful observation. Currently, the evidence gathered serves to illuminate two key realities: the significant limitations inherent in our current astronomical observation capabilities and the extraordinary, puzzling nature of Atlas itself. It is as if almost all the pieces of a complex puzzle have been assembled, yet the complete picture remains frustratingly elusive. The object's subsequent movements and interactions will be determined definitively by recorded data, not by conjecture.
Observing Atlas now is like watching a live-action film where the final act has yet to be written, its conclusion unfolding in real time before our eyes. The cosmic countdown persists, and within a matter of weeks, humanity will stand on the precipice of revelation. Are we bearing witness to the most perplexing comet ever recorded, or is this celestial visitor poised to irrevocably alter our comprehension of universal possibilities? The profound silence enveloping the vast expanse of space resonates with an intensity that feels almost deafening. Amidst this tension, the central lesson emerging from the saga of Atlas crystallizes with striking clarity. It fundamentally teaches us that the universe operates on principles far stranger and more enigmatic than our terrestrial perspectives often allow us to conceive. This extraordinary phenomenon serves as a potent reminder that intellectual humility is paramount. We must continuously interrogate the foundational assumptions we hold dear. Our default inclination is to categorize distant cosmic objects as natural phenomena, specifically comets originating from the fringes of the solar system. However, the accumulated data defies easy categorization. The object's erratic and seemingly purposeful trajectory, the presence of an unexplained phantom mass detected through gravitational anomalies, and the timing of its conspicuous signal blackout together compel us to entertain propositions that, until now, belonged solely to the realm of speculative science fiction. This unfolding mystery eloquently demonstrates that authentic scientific endeavor is less about possessing definitive answers and far more about the courageous pursuit of the most challenging questions. It demands an unwavering commitment to following the evidence wherever it may lead, regardless of the potential discomfort or revolutionary nature of the conclusions it might dictate. Whether Atlas proves to be a primordial fragment of cosmic rock or perhaps something entirely different, a probe of unknown origin, its existence constitutes a profound and humbling reminder. It urges us to nurture our innate sense of wonder, to cultivate relentless curiosity, and to maintain vigilant observation of the heavens above. The ultimate question remains suspended in the vacuum. Is this occurrence the manifestation of a one-in-a-billion natural coincidence, a cosmic fluke of staggering improbability? Or does it represent the unmistakable signature of intelligence far surpassing our own? The possibility compels contemplation and fuels the enduring fascination with the cosmos.